Hello students, this video is about the client-centric consistency. Why to replicate data in distributed systems? Data should be replicated to enhance reliability and to improve the performance. But if there are many replicas of the same thing, how do we keep all of them up to date? And also, how do we keep the replicas consistent? Consistency can be achieved in a number of ways. We will study a number of consistency models as well as protocols for implementing the models. More on replication. Replicas allows remote sites to continue working in the event of all local failures. It is also possible to protect against data corruption. Replicas allow data to reside close to where it is used. This directly supports the distributed system's goal of enhanced scalability. Even a large number of replicated local systems can improve performance. Think of clusters. So what is the catch? It is not easy to keep all those replicas consistent. Data-centric consistency models. A data store can be read from or returned to by any process in a distributed system. A local copy of the data store can support fast reads. However, a write to a local replica needs to be propagated to all remote replicas. So these are the different processes shown, and all these processes are connected to the distributed data store, and every process is having access to the local copy. Client-centric consistency models. Another class of distributed data store is that which is characterized by the lack of simultaneous updates. Here, the emphasis is more on maintaining a consistent view of things for the individual client process that is currently operating on the data store. More on client-centric consistency. How fast should updates or writes be made available to read-only processes? Think of most database systems, mainly read. Think of DNS. Write-to-write conflicts do not occur. Think of www as the DNS, except that heavy use of client-side caching is present. Even the return of stale pages is acceptable to most users. These systems all exhibit high degree of acceptable inconsistency, with the replicas gradually becoming consistent over time. Towards eventual consistency, the only requirement is that all replicas will eventually be the same. All updates must be guaranteed to propagate to all replicas eventually. This works well if every client always updates the same replica. Things are a little difficult if the clients are mobile. Eventual consistency, mobile problems. That is, if the user is mobile. The principle of mobile user accessing different replicas of a distributed database. When the system can guarantee that a single client sees accesses to the data store in a consistent way, then we say that client-centric consistency holds. So in the diagram, it is shown that client is moving to another replica. So there are some problems for the mobile users related to the consistency. The problems are: 1. Increased latency due to mobility. When users move between different regions, they may interact with geographically distant servers or data centers. This can increase network latency, which causes delays in synchronization. As a result, users may experience out of date data for a longer period of time, leading to inconsistencies in their view of the system. Example, a user moving from Europe to the US might continue to interact with a European server, causing longer delays before updates are propagated to nearby US servers. The longer it takes for updates to propagate, the longer users might see stale data. Second issue is partitioning issues. Mobile users frequently change networks. Example, from Wi-Fi to cellular or from one city to another, which can lead to network partitions. When a network partition occurs, the user's device may temporarily lose connection to certain parts of the distributed system, making it difficult to receive updates or propagate changes. Example, mobile users frequently change networks. Example, from Wi-Fi to cellular or from one city to another, which can lead to network partitions. When a network partition occurs, the user's device may temporarily lose connection to certain parts of the distributed system, making it difficult to receive updates or propagate changes. An example, the Bayeux system. The Bayeux system implements four models of client-centric consistency: monotonic read consistency, monotonic write consistency, read-your writes consistency, and writes follow read consistency. The Bayeux system. First one is monotonic reads. If a process reads the value of a data item X, any successive read operation on X by that process will always return that same value or a more recent value. Monotonic writes. A write operation by a process on a data item X is completed before any successive write operation on X by the same process. Read your writes. The effect of a write operation by a process on a data item X will always be seen by a successive read operation on X by the same process. Writes follow read. A write operation by a process on a data item X following a previous read operation on X by the same process is guaranteed to take place on the same or a more recent value of X that was read. Distribution protocols. Regardless of which consistency model is chosen, we need to decide where, when, and by whom copies of data store are to be placed. Dotted lines indicate the client-initiated replication and solid lines indicate the server-initiated replication. Replica placement types. There are three types of replica. Permanent replicas tend to be small in number, organized as cluster of workstations or mirrored systems. Second category is server-initiated replicas, used to enhance performance at the initiation of the owner of the data store, typically used by web hosting companies to geographically locate replicas close to where they are needed most. And third category is client-initiated replicas, created as a result of client requests. Think of browser caches. Works well assuming, of course, that the cached data does not go stale too soon. Update propagation. When a client initiates an update to a distributed data store, what gets propagated? There are three possibilities. Propagate notification of the update to the other replicas. This is an invalidation protocol which indicates that the replica's data is no longer up to date. Can work well when there are many writes. Transfer the data from one replica to another. Works well when there are many reads. And third one is propagate the update to other replicas. This is active replication and shifts the workload to each of the replicas upon an initial write. These are the references used for the contents.